Hello, everyone. A very good morning to those who are joining us from Singapore and Asia, and good afternoon or good evening to all of you joining us from other parts of the world. Thank you for being here with us for today's online event. My name is Jin from SGInnovate, and as a Singapore government-backed investor, we have been building up and driving deep tech innovations in AI, healthcare, quantum tech, and autonomous technologies across various industries. A big part of our work is also to build a strong deep tech ecosystem through the events that bring people together to our community, including experts and key thought leaders like Google Health and our local eye experts in today's session. Today's online event is a special one as we host the EyDIA Journal Club, a monthly AI and digital innovation-based international virtual eye journal club initiated by the AI and Digital Innovation Group of the Singapore National Eye Centre and Singapore Eye Research Institute. At this session, we will get insights on AI and digital innovation in eye, and we encourage you to engage with our presenters during the session by submitting your questions in the Q&A box located on the lower panel of your screen. Without further ado, I would like to invite Daniel from the Singapore Eye Research Institute to start us off. Daniel, please.
Thanks, Jean. Hi everyone. Hi, hope you guys can see me. Yeah, I mean, this is the second, welcome to the EyDIA Journal Club. This is the second time that we have done after the one we did last month with Professor Michael Cheng. And thank you, SGInnovate, for agreeing to be our excellent co-host to actually organize this the event today. And I must say that I'm actually very blessed to have met many friends over all these years. And today I actually managed to have 4 superstars, 2 from the AI space and 2 from the eye space to really share some of the basic stuff on AI, machine learning and deep learning. You know, the topics of, you know, I mean, the hot topics that we have been exposed to over the last few years. In fact, I would say that this is especially during this COVID pandemic crisis period, the use of digital technology, AI, Internet of Things, and I feel many people are very interested to kind of learn a bit more to see how we could potentially use these some of these state-of-art technologies in the clinical practice. And to start off, we have 2 the Google AI friends that I had met, whom I met actually a few years ago, and they really were the trailblazer in spearheading some of these AI work in not just ophthalmology but in the whole healthcare settings. And we have been also collaborated very closely in terms of writing major review papers and stuff, discussing some of the barriers and for implementation, the ethical issues and stuff like that over the last few years. And then I have 2 other big professors in eye whom I've actually known since day one when I study ophthalmology, and they're still here. And I have never thought of one day I would be, moderating the same session with them in the same symposium. So, I mean, today is a very lucky day for myself, I must say. And without further ado, and I see Dr. Yun Liu is here, and then he's actually really gonna kickstart the program. And then he's also someone very special who's also originally from Singapore, who have also migrated. I'm not sure whether migrated as yet, but then he has actually gone to US and did his PhD in MIT, Harvard, and then has then signed up with Google to be one of their senior scientists right now. And then we also have Dr. Lily Peng, someone whom I also, I mentioned just now. Lily and I, we have went around the world and speak in many journal clubs and, symposium, instructional courses. And in fact, sometimes I wonder whether I'm one of the Google team members, because, it's really fun to hang out with the whole team, just at work and after work. And I would save the introduction for the 2 professors later after Dr. Yun Liu and Dr. Lily Peng's talk. So Tuan, do you have anything to introduce about SGInnovate? Perhaps you want to share a little about SGInnovate, or Jean? Yeah.
No, well, I've introduced SGInnovate a little bit
Okay.
to you
Okay. All
already,
right. You're
so I think
okay.
that's
All right.
fine. Yeah.
All right.
Yes, why don't let's just continue with Dr. Lindu's presentation then?
Okay. Let's do that.
Yeah.
Yeah.
Mm-hmm.
Okay. Yun, all over to you. The stage is yours.
All right, thanks, Dan. Thank you for the very kind introduction. As Dan mentioned, we've known each other for a few years now, and it's always a pleasure to meet him and go to conferences and have deep discussions about AI for healthcare with him. So today, the title of my talk is to develop and evaluate machine learning models for healthcare. And just as part of a standard disclaimer, I'm an employee of Google. So before we start, let's first ask the question, what is machine learning? And this question seems simple, but as Dan actually gave the perfect introduction just now, he mentioned three terms: artificial intelligence, machine learning, and deep learning. And these three concepts are related, but not exactly the same thing. Artificial intelligence is a project to build non-human intelligence. So how do you get machines to do things that you think would require intelligence? Machine learning is one of the ways to do so, but by getting the machine to learn from data to get better at a specific task. Now, deep learning is a specific kind of machine learning, which has gotten more popular in recent years. And the reason it's called deep is because the computation within the model is done by multiple layers of computation. And so the deep refers to the number of computation and the fact that it's arranged in layers. So a few decades ago, deep learning actually existed in a different name called artificial neural networks. And what's changed between the 1980s and 90s and now is the fact that A, we have more compute. B, we have slightly fancier architectures, and architectures means how you arrange the computation. And three, we have more tricks for understanding how to train these models. And lastly, we have much more data in many arenas. The main benefit of having artificial neural networks or deep learning is to get more accurate models. And because the model is learning on its own from the data, you do not have to do what's called feature engineering. So feature engineering means that one needs to specify what it is that's predictive before one passes the data to the machine. Now, machine learning is actually everywhere around you. And there are many products that Google has created that many of you might have heard of or used that actually uses machine learning or some sort of deep learning to help create its functions. So one example is Google Photos, where you can actually type a dog or a cat. And this allows you to actually find photographs of dogs and cats within your album without actually you going in and labeling each photo individually. Another example is in Gmail or Inbox, where you might have noticed that sometimes as you're typing emails, it gives you suggestions of how to reply, and in other examples not illustrated here, suggests the next word or to help you complete the sentence. All of these are powered by machine learning to get the machine to help and understand what it is you're saying and what it is you want to do next. So let's switch over to medicine. Now, algorithms are not new in medicine. And by algorithms, I mean a way of doing something. And if we think about it, algorithms are essentially taking data as input and then doing some computation on it and then outputting a prediction. So let's look at a real life example of a risk score. Now, a risk score in medicine just means that we first understand, let's say, a patient, and we extract certain what we would call features in machine learning from them. So one example of a feature is this patient more than 75 years of age? That's either a 1 or a 0, depending on what the answer is. Same thing for the female and whether they had a prior stroke. Now, inside the model, in this particular case, the computation that's happening are to multiply each of these inputs with a corresponding weight. Each weight is a numerical number that represents how important that particular input feature is to the final output. Now, as this model does these multiplications and sums them up, it gives you an output. And that output, which is another number, is the risk estimate by the model. Basically, no matter how complicated your models are, this is what they're doing. There is a box in here that is taking the input, integrating them, and computing some mathematical functions, and then outputting a number. Now, generally, when we have these models, the way they are evaluated is to first consider what is the right answer. And the right answer can be called the ground truth or the reference standard. Now, this is not as straightforward as it sounds, and I'll give you an example from our own work. So here's one example. Each of these colors represent a specific grade of eye disease. Each row is a single patient's image. Each column is a person grading the image. What we find, and here's an example where we've highlighted one of the rows, this row contains each of the 5 colors. What that means is that this same image, when read by different graders, was read by any, was interpreted as any of the classifications that's possible. So that's not desirable. But what that means really is the fact that different readers can disagree even upon seeing the same input image. Other aspects that are considered in this process of validation is to look at the case spectrum, which means what kind of patients are going into the model in the data set that's being used to evaluate the model, and whether the validation set that you're using is independent of the data set used to develop the model. 2 more aspects here are A, what do you use to actually do the evaluation? What are the metrics? Is it the AUC or is it something else? And are those metrics meaningful and are they useful in this context? And the last thing that's often forgotten when we're doing a lot of these complex work is what is the impact that having such a model will have on the actual patient management? Like, does it benefit the patients, the clinicians, or someone else? So all of that still matters when we're talking about machine learning and algorithms or models based on machine learning. But some things are actually a little bit new. So let's examine why. First of all, when we last looked at an example for medicine, the risk score only had a few weights or parameters within there. For example, the first weight might just say that age is important to some degree, and the second says being female is important to some degree. In machine learning, we often have way more parameters than that. So here's one example. Let's say the input is an image here. It goes through many layers of computation in this deep learning setup, and then it outputs a single risk prediction. What's happening in each of these layers is a repetitive process of multiplying and adding numbers. So here's one example. Let's say we're looking at the input layer, which is an image. The image, when we look at it in the computer, is usually comprised of large matrices of numbers. So it's a grid of numbers, and there might be multiple layers to this grid because these images, if they're color, will have a red, green, and blue channel. And depending on the medical image you're looking at, they may have different numbers of channels, or the numbers might have different granularities. They can be integers, or they can be more precise floating point numbers. In this layer, these numbers will be multiplied by a set of other numbers to produce some more output. Now, this process repeats itself over multiple layers and before you get to the final risk estimate. Now, this is a toy example. Let me show you what a real example looks like. So here what we have is the input image on the left and a series of computations in the middle before we get to the output prediction of the severity of diabetic retinopathy. The colors are indicated here, but essentially the high-level takeaway here is that each of these colors represent one block of computation that we just saw, and different kinds of colors represent different kinds of operations. In this particular case, this network has a few million parameters and billions of operations. Now, the machine is learning what kinds of operations to do by itself. How do we know what it's actually doing? Well, it turns out that there are techniques to extract what it is that the machine learning models have actually been learning. So here's one such technique. If we look at the earlier layers in this example, it turns out that the earlier layers are learning simple textures and edges. So if you look here, these are all little wavy lines. And what it means is that these are the wavy lines that most get those computation sort of like excited by this particular input. As we go up in the layers, what tends to happen is that the features and the concepts that are learned tend to get more and more complicated. So for example, here we go from edges, textures, to more colorful patterns. Right at the top over here, what we're seeing is that the model has now learned how to recognize parts of objects. At the very top, what the model is then doing is to take how much the input image resembles each of these concepts that it has learned, and then use those elements to then make a prediction about the image overall. Now, it does get a little bit more complicated than that. And what do I mean? Well, I mentioned that the machine learning models are learning from data. Now, the problem is that if you feed the same data into a machine learning model, it actually might learn different things. Here's one example with red and blue dots, each of which is one category. And the objective of this machine learning model is to learn how to separate the blue and red dots. Now, it might learn anything ranging from this straight line to this curve to this fairly convoluted line on the right over here. Now, if we look at this, one might think that the right answer might be something like what's in the middle. The answer on the right, this convoluted line over here, might actually be overfit. Overfitting means that if we get a new point over here, let's say there's a new point right where my red cursor is that point supposed to be a blue point or a red point? The model might actually get it wrong because it has learned such a fine-grained pattern over here in terms of the separation line between the two. So that is overfitting. So let me give you an example where folks have conducted experiments to understand how overfitting happens. And in this case, this was an example where the model was being trained to understand whether an image is one of 10 categories. Some examples of the 10 categories were dogs, cats, and cars. The blue line over here is if we train the model using the actual labels. So a picture of a cat is actually labeled as a cat. What we see here is that as the training of the model proceeds, it goes down, and it goes down to near zero. What that means is that the model has successfully learned to recognize what's in the training set. Now, what's shocking is that what happens if you scramble the labels? So an image of a cat is now labeled as a car, an image of a dog is labeled as a cat, and so forth. So that's this line, the red line that says random labels. So what happens there, astonishingly, is that it learns more slowly. Instead of going straight down like this, it takes a while to go down, but it actually does. And eventually it goes down to near zero as well. What this means is that the model has somehow learned to distinguish what is in the training set, even though the input images have nothing to do with the labels. This by itself is not a problem. What is then a problem is that if we now take that model and feed it new data and evaluate its error, it turns out that that particular model has an error of 90%. Now with 10 categories and it's balanced, it means that 90% means it's randomly guessing. It hasn't learned anything that's useful outside of that synthetic training set it has seen before. So the way to prevent this is by tuning the models properly. To tune the models, there's something called hyperparameters. And each hyperparameter is sort of like a knob that you can turn to change what the model learns. So the takeaway here is that a certain hyperparameter setting plus a given data set will give you a trained model. These are the ingredients to a machine learning model that's being trained. Now, these knobs change, what the model learns. And so specifically what that means is the parameters that's been learned by the model, all of those numbers you saw in those little grids previously, those are being learned automatically by the model. And when those weights are changed, that changes the resulting performance. And the way tuning actually proceeds is by actually saying, let's try setting A, let's see if it works, let's then try setting B and C and so forth. By trying a number of different settings, one then picks the setting that gives you the best performance. Now the problem is that to do so, if you do it straight on the training set, you will observe exactly what we saw previously, where the model can overfit and learn to fit the training set exactly without generalizing. The way to avoid it is by ensuring that in addition to a training data set, you have a separate tuning data set. Now, let me emphasize again, this is not directly with the validation set. One thing to take note of at this point is that there are different terminologies for what these things are called. Specifically, what's called a validation set is actually completely opposite depending on which literature you're reading. So in the clinical community, for example, a common way of understanding risk scores might be to call things a development set, and then you test things on a validation set, hence the word validation. In the machine learning community, what you will see often is that they will have a train set, a validation set to find the best hyperparameters, and there are a test or holdout set that's used to look at how the model is performing on independent data. Now, we don't have a great solution for everyone right now because these fields coexist together, but we feel that it might be less ambiguous to use more standardized terminology. In any case, no matter what terminology you choose to adopt, what's most important is to understand what it is that the study is doing. One final note, you might see a term in the literature called cross-validation. This actually means that the training and validation splits are actually being repeated a number of times. You need to be careful when doing this because it's very easy to accidentally and unintentionally tune the hyperparameters directly on the cross-validation folds. Now let me go back to this diagram that you just saw, where we had 3 models trained on the same data with very different kinds of separating lines being learned. I previously mentioned that the one on the right might potentially be overfit. What I want to say now is the one on the left is also problematic. It's actually what we call underfit, potentially. What that means is that we might be leaving some performance on the table because the line that we see is not optimal for the data that we are using. So what's important here is that machine learning is actually an exercise of carefully balancing overfitting versus underfitting. And the way to do that, or at least one of the ways to do that, is to make sure that you're using the right kind of machine learning model to begin with. So one that we have been discussing quite a bit is deep learning, but there are many other kinds out there. And we don't have time to get into the details, but generally speaking, with the one that's the right one to use for that particular problem depends on how much data you have and what kind of data they are. So more complex kinds of data tends to require more complex kinds of machine learning models. So now let's put it together and look at some actual examples of studies. So first, let's look at a traditional risk score study and how it's developed. There's a lot of boxes here, but it's actually quite simple. If you look on the left, this whole section here, there's input data and the labels. It is being used to develop a risk score. This part of the data is called the development set. On the right over here, there's actually 2 data sets. And this is important because usually we want to understand if it generalizes, and we can use multiple data sets to do that. And so essentially the takeaway on this slide is that in a traditional process, it's a development set, and there's one or more validation data sets. Now let's look at what happens for a machine learning study. It gets a lot more complicated, but very briefly, it's actually mostly the same thing. On the left over here, this whole thing here is the development data set. The only thing that's changed, really, is the fact that the development data set has now been split into 2. One, that's the training data set, and 2, that's the tuning data set. The entire process of machine learning hyperparameter tuning really happens in a loop by training a model, trying it on a tuning data set, and then repeating until you find a set of hyperparameter settings that works well. Finally, in the validation phase, it actually looks very similar, where you might use one or more data sets to validate the model. So now let's talk a little bit about what happens beyond just validating the model. So here's an example where we have an input fundus image, and this over here is the model's output. The ground truth, which is the actual answer, is over here. And in this case, here are the 5 categories. The model actually agrees with the ground truth. So the model thinks it's this last category over here. These pink dots are graders who have looked at this image and provided their own interpretations. In this particular case, all 3 graders provided very different interpretations, and none of them agreed with each other. In this case, as if we showed 3 other graders the same image and the model's prediction, it actually helped them all arrive at the same answer. Let's look at a second example. So here's another example of an input fundus image. And this time, the model is a little bit uncertain as to whether it's the first category or the third category. In this case, the ground truth is the third category. And before seeing the model, the unassisted graders actually mostly thought it was the first category. With the assistance, these graders actually all agreed that it was the third category, which turned out to be correct. Let me show you a third example, but this time let's change things up a little bit. Instead of just showing the graders just the input image, along with what the model thought it was, let's try and explain what the model was doing. So over here, here's the input image. In the middle over here, you're seeing a grayscale image, so in black and white, but with green dots on where the model was most important for predicting its prediction. In this case, the model thought that it was the third grade as the most likely, and it's using these green areas over here to do the prediction. Now, it turns out for this image that without seeing any of this, the graders thought it was, again, 3 separate grades. But if we show them both the model predictions, as well as this image over here, which shows them how the model is looking at the image, this helps the graders arrive at a single consensus. So here are the takeaways. First, whether you are using machine learning or not, you need to design the study well. And there are multiple components to this. The first, make sure you're working on a problem that is going to help the patient care pathway. Second, make sure you're studying the patient population that's relevant for this problem. Third, make sure you're looking at the right kind of ground truth and that it's rigorous and not highly variable. If it's variable, you might need to do things like getting multiple graders to look at each image. Lastly, make sure you're using the right metrics for the problem. Now, the important part of this talk, machine learning is really about balancing overfitting and underfitting. And many of the things that you're seeing, different techniques, are actually about balancing the two. And a large part of this actually is about avoiding overfitting. But what's important to know is that it's also possible to be underfitting. Make sure you use the right machine learning model to avoid some of these problems, and also make sure you're tuning the model on an independent data set, whatever you choose to call it. Lastly, ensure that the model you're using is helpful to users, and that might involve way more than just the machine learning validation itself. You might have to be looking at how do you present the results to the users. So thank you for your attention. Here are 3 articles that we've written recently that you can learn more at.
Thanks, Yoon. That was a great talk. I mean, I hope that, we could actually have you, speak more in the coming years. I mean, this is totally all the very, very important basics that I think anyone who wants to do AI research should actually know. And I also appreciate that you have actually gone from the simpler ones to the more complicated ones, and I personally also has refreshed some of my memories as well there. Okay, thanks once again to speak, and then without further ado, I will actually get the second speaker, Dr. Lily Payne. I think she actually really needs no further introduction. I mean, I think she's an AI superstar now that I believe everyone around the world knows her really well. Regular, I mean, she gives a TED talk that I personally feel inspired after listening to them. I know. Well, so for those of you who don't actually know Lily, Lily was a Stanford grad. She did a chem engineering there, and then went on to UCSF to do her MD PhD. And then prior to joining Google, she also tried some entrepreneur careers with a startup called Nano Precision Medicine, if I'm not wrong. And yeah, so I mean, she's right now, I think, one of the senior product managers in Google, and I would let her share what has Google done over the past few years and what some of the things are currently in the pipeline as well. Lily, please.
How's that? Thank you so much, Dan, for always the glowing and very flattering intro. I'm not sure I can live up to all of that, but can everyone hear me? Yeah. And can everyone see my slides?
Yep.
Okay, excellent. So thank you guys so much for inviting me. So Yoon and I work on the same team. So just to let everyone know, I also am a Google employee. And while Yoon spent some time talking through, the basics of AI, I'm going to spend a little bit of time talking about how do we actually implement AI and what are the barriers to implementation in real life settings. So let's just kind of start off with the presentation. As everyone kind of knows, deep learning is really truly all around us, Yoon gave a few examples of things that are happening at Google, but we can see this actually being a core technology in many, many companies, so not just within Google. And in fact, the technology has been shown to be quite useful, potentially useful, for many healthcare challenges. So in example, in eye disease, and also with SERI's own work as well, in skin cancer and in breast cancer. And the best part about this is that the technology works in the hands of not just expert research scientists like the ones that we have at SERI, but also in undergraduates, business owners, and even in some cases this high school student here who built his own algorithm that helps diagnose breast cancer. So and in the recent years, because of this potential, we've seen this huge increase in the number of papers at the intersection of deep learning and healthcare. So this is a very fancy graph that I generated by Googling in PubMed, or not Googling, sorry, searching in PubMed, the intersection between, like deep learning. And you can see that this has increased about 130-fold. Of course, given the adoption of deep learning-based technologies in consumer products, and these exciting use cases in healthcare, one would expect that we would have many AI-enabled products in the healthcare space. But, as always, translation into product is pretty slow, and there's always this gap between expectation and reality. And so hopefully I'll talk about 3 of the things that I've seen that seems to contribute to this gap. I'm sure there are many others, and we can talk about what those are in the discussions as well. So the 3 common myths that, in my view, in terms of in building and translating AI models is the first one is more data is all you need for a better model. The second myth is an accurate model is all you need for a useful product. And the third myth is that a good product alone is sufficient for clinical impact. So we'll unpack each of these as we kind of go along. So focusing on the first one, more data is all you need for a better model. I think one of the things that we've learned as we're training more models, it's that it's not really just more data, it's really about the quality of data as well. And so what I mean is, so a few years ago, we set out to explore if we could train a model to classify fundus images for a disease called diabetic retinopathy. And this work involved, working with, 54 ophthalmologists, providing labels, over 100,000 images. And so you could see here that, on a set of 100,000 images, we actually got about 900,000 diagnoses. So you're probably wondering what's going on. So this brings us to our first myth, which we kind of unpack this a little bit more, is that we actually got multiple labels for these images because they're, as Yoon kind of said, the diagnoses kind of change based on the doctor's opinion. And what we found was that usually the more labels we had, the better, kind of the algorithm. But it's also how you label and the type of data you have. And so really when we think about data and labeling strategy, that high quality and high quality data and an efficient labeling strategy is really the key, right? So, so this I'm pulling out actually figure 4 from the paper that actually resulted from this work, and this is a particularly useful figure that I don't think gets the credit it deserves probably because it's number 4 and not number 1. And what we find here is that that at some level, at a certain level of data, there's actually kind of diminishing return. So I'm going to go over this first panel here that illustrates this. So in panel A, we're looking at how an algorithm performs based on the number of images in that data set. So each of these dots represent a different model that was trained based on the size of the data set. And you can see the performance, which is on the y-axis, really saturate around 50 to 60,000 images. So what we learned after we labeled 130,000 images was that for this particular problem, a training data set of about 50 to 60,000 images that are well labeled could have given us very similar algorithm performance, and that 130,000 wasn't totally necessary. It doesn't mean it generalizes for every problem, but in this particular problem, it was actually a really good sizing exercise for us, and really serves as a good starting point for other problems like this. The second panel, in panel B, we actually measured the performance compared to the number of images per grade. So as I kind of alluded to, we did multiple grades per image. And so the development set had an average of 4.5 labels per image. And so the interesting thing was, while the increasing in the number of labels in the development set, in the training set, didn't seem to change performance all that much, the tuning set had a really big impact. And in fact, what the takeaway from this figure is that if you had limited resources and you could choose between labeling the training set or what we call the tuning set, in some places we call it the test set, but I'm going to use tuning set just for consistency right now, that we would actually invest in the tuning set rather than the whole training set. So you could actually get a few thousand images, get it labeled really well, and have very good results as well. So we took these insights and again demonstrated in multiple subsequent papers that you could, again, in this case, instead of increasing the number of labels, we basically put 3 specialists in the room and had them argue with each other to what the ground truth is. And so but we only had to do that for a few thousand images, not hundreds of thousands of images, to get very, very good performance. Okay, so that's the first myth. All right, so we're going to move on to the second one, which is an accurate model is all you need for a useful product. So really, the key myth here is really it's not just about accuracy, but it's also about usability. And so what I mean is that building a machine learning model is just one step in preventing blindness with AI. So the model is like kind of the engine, but you actually need to build out the whole thing to have a car that's functional, right? So similarly, the model needs to be incorporated into a product that integrates well with IT systems and is actually usable by doctors and nurses. And it's also critical that this product actually fits well into a clinical workflow. So this is an area where our team did, and others have been starting to gather lots of evidence around this. I'm going to highlight a little bit in particular our work in Thailand, where we worked with Dr. Paisan from Rajaviti Hospital, and we conducted both retrospective and prospective validation studies. So based on the generalizability of the algorithm we demonstrated in retrospective studies, we started in late 2008 in prospective studies to evaluate real-world performance and feasibility of deploying AI into the existing national screening program. And earlier this year, we closed recruitment of about 7,600 participants who were screened using AI across 9 different sites. So we're analyzing the data, and some of the early results kind of show that what we've learned really is that this human-centered approach is key to building useful products. And so this figure we have here is actually the work that our HCI and UX team, so the human-computer interaction experts and user researchers, they actually went and mapped out what every person that was involved in a DR screening encounter, what every person was doing. So from the nurse to the patient. And this really helps us identify potential efficiencies and inefficiencies, so bottlenecks, as we help implement the software. I think this paper was published as a part of CHI proceedings. And so this is an ongoing piece of work, and in terms of understanding workflow. But what we really found was that, we have to not only cover accuracy, but really product functionality, and then design workflows around these products to maximize its potential. Okay, so this brings us to the last myth, which is a good product is sufficient for clinical impact. So I'm a product manager, and we're all about good products, but really at the end of the day, we actually have to study the impact on the system. And so concretely, what I mean is we can have the best product in the world, but if patients can't access it, you've done no good, right? So for example, one of the reasons that people don't show up for screening in specialty eye hospitals really has nothing to do with product at all. Some patients in India, for example, where we've done some work, actually take a day-long or half-day-long trek to the hospital to get that screening done. And for some folks, that means getting someone to take care of their kids or coping with a days of lost wages, which is a lot of money. And so screening doesn't happen because it's not really about I don't care about my health. It's if I do this, I won't be able to take care of my family. And so that's kind of a terrible choice to have people make. And so we think that screening, AI enabled or not, if we can move them closer to where patients live and work, means that the screening can be done efficiently and easily. And that means that then this choice of having to take care of oneself versus loved ones is not really something that people have to grapple with as much. So that's one aspect of just almost. I mean, I know I was spending a lot of time on transportation, but it's not just in India, but in the US and other places, we find transportation being one of the biggest blockers to people getting screened and following up. There are some communities in the US where these are people who actually have vision-threatening disease, and we see follow-up rates of 15% because of transportation and logistics. Okay, so lastly, of course, all of these screening programs must be paid for in some way, and therefore cost-effectiveness research is really critical in adoption. This includes how a product should be implemented to take into account the downstream effects of not just the cost of screening, but the cost of follow-up and treatment. And here is an example that Dr. Wong and his team at SERI did publish. This is a paper that was published recently in Lancet sharing the results of an economic modeling study comparing different deep learning approaches, automated, semi-automated. And so, this is really interesting. And in fact, actually, one of the most interesting things about this is that the semi-automated approach or assisted approach was actually more cost saving than either alone. And so it's really exciting to see the beginnings of this research come out, especially pioneering this type of research at SERI. And we're looking forward to emulating this and putting more out there, because I think this is going to be a very critical component into scaling these solutions. So in summary, I hope I've kind of covered the 3 common myths of building and translating AI models, and I'm pretty sure these are not the only ones. And so, going in summary, the first myth is that more data is all you need for a better model. And we really think that label quality and ground truth is critical to building that accurate model, not just the quantity of data. The second myth, that an accurate model is all you need for a useful product, really think that should be that a human-centered approach is also required to build a useful product. And of course, the third one is that a good product is sufficient for clinical impact. And we really think that implementation and health economics is critical to adoption of AI products. All right, I'm going to flash up some references. Thank you very much for having me.
Thanks, Lily. Another very exciting talk that I attended again. I mean, I must say I haven't actually seen this. I've seen you speak multiple times. I think these sets of slides are new, so that's great. And and thanks, Yoon. So I mean, we're going into the next sections where we're gonna have a Q&A with all the AI experts as well as the clinical experts. And I also want to leverage on this opportunity to introduce 2 very well-respected, internationally renowned eye giants, Professors Dennis Lam, as well as Professor Tin Ong. Here is really lucky to have them to join us in their very, very busy schedule, managing, the different eye institutions as a senior leadership, playing the senior leadership role. So let me see. Professor Dennis Lam, hi. So, I mean, just a very brief introduction. I mean, if I were to go on to introduce Professor Dennis Lam, I'm going to spend hours and hours. But just in summary, he's actually recently been ranked the top 100 most influential ophthalmologists in the world. And then he's also the ex-president of APAO and APVRS, and currently serving as the editor-in-chief for APJO Journal, and also the Secretary General of AAPPO and APMS. So both the Asia Pacific professors of ophthalmology. So he's the boss of all the professors in Asia Pacific, as well as serving as the Secretary General in the Myopia Society as well. So he's currently founded the Hong Kong CIMA International Eye Care Group, and I will probably ask him to share a little about that, and then I'm going to go on and ask him another questions about how AI has revolutionized the field in both Hong Kong and China. Yeah.
Hi, Dan. Yeah, first of all, my deep gratitude for inviting me to participate in these very exciting programs. I think in terms of these AI stuff, I think it's really something extraordinary, something exciting, and many of us will consider this to be something that can lead to the fifth industrial revolution. And of course, in healthcare, it will be much affected. And I think this will change the landscape of healthcare, including ophthalmology, in the coming 1 to 2 decades. There will be substantial changes. And if you're talking about what are the essential components, I think number one is whether we have the technology, because the concept has been there, but if you are not backed up by the technology, including the big data and then the 5G, so on and so forth, then you are hand-tied. So the technology has come, and then whether there's such a need depends on the different places. Some countries, the need is higher, some countries, the need is lower. But overall speaking, I think you cannot escape from AI in future in healthcare. So this, I would say that there's a huge need overall speaking. And number three, I think it's also very important is the regulatory component, because this will involve a lot of patient privacy, the ethical part, and then the governance, so on and so forth. So I think these are some of the basic components. And in terms of the scope in ophthalmology, number one is obviously diagnosis. Yeah, the diagnosis of a particular disease, and then the prediction of a disease coming along or not, and also the monitoring of the progress of the disease. So this is one major part. On the other hand, actually, you can integrate this into robotic surgery, through telemedicine. So in a long distance, far away, you can still do surgery at home. So I think this sort of some of the major scopes. And if you're talking about the development in China, then we go back to these basic parameters, technology. So I think we all agree that China is one of the forerunners in terms of these information technology, 5G, big data, and AI, so on and so forth. So we do have the technological backup. And number two, whether we have such a need or not, I think in towns or villages, the medical resources are below enough. So through this AI, then you can solve a lot of problems. So this gives a very strong incentive for the government. So I think in China, the government has sort of special groups to study this, just part of the FDA. For example, you have a AI, product. So they have to, this is all something new. So they have to classify this into different categories. Can this replace the role of a doctor, or they are just something, giving a good assistance to the doctor, so on and so forth. So I think technology is okay, the niche is huge, and then regulatory stuff. So China, I think, is one of the forerunner because there's such a huge need. And not just about whether this is advanced or revolutionary or not, it's cost saving. And it's not just cost saving, because You cannot do that. You cannot extend your surface from the first-tier cities to the rest of China. So in terms of politics, because in many places, politics comes first. And then actually politics in China is serving the people. When there is such a need, the government has very strong incentive to do that. So if you are talking about the actual situations in China, number one, we have a number of companies. They have the products for this diabetic retinopathy and assisting the diagnosis. So it's quite a few companies who have already got FDA approved. And then before the approval, for example, to the best of my knowledge, there's one tied in with a community project with Life Express. So they bought fundus cameras and they put this in remote area. And then they have collect all this data and has been there for quite a number of years. And I think one of the issues mentioned is the accessibility to patient. China is a huge place, 1.4 billion populations. But then the infrastructures is particularly good. We have the high-speed train covering all over China. And then from the high-speed train, we have highway. We have good road constructions to really, small town. And China is undergoing a revolutionary urbanizations. So that means the accessibility down to these small places is quite sort of rich. And also they are densely populated. In China, you're talking about a city. A city you can have maybe 50 million populations. Yeah, and then for like Chongqing is over 50 million population, and then you are talking about a small county. It's many of them are over 1 million populations. So all these are basic ingredients that can give a very good background for AI to develop there. So I think in China, from diagnosing cataract to glaucoma, macular diseases, so on and so forth. So this is a major sort of national incentives. We're talking about innovation, tie-in with these AI, big data, so on and so forth. So all over China, we have so many provinces, so many leading universities. Many of them have set up special group and put up a lot of resources, injecting all this into these innovations. So I think if we look down the road in another 5 years, then I think a lot of exciting new developments, including products, will be there. So it's not just about diagnosis. In China, they have already started the remote robotic telesurgery. So it has already been done. Of course, this is the initial stage. We do expect a lot more advancement and refinement in future. But by and large, I think the climate in China, they are very, looking forward to this exciting area. And I believe now the technology is there, we'll be advancing further. The need is there, and then the government in China, they have really special attention. So they are, instead of wait and see, they're actually pushing everybody to go there. And for example, in our hospital, by the way, you talked about SEMA. So I left Chinese U in 2012, and then I started a clinic in Hong Kong, and then pretty soon I started eye hospitals in Shenzhen, just across the border. And a few years down the road, in 2018, our company has been listed in the stock market in Hong Kong in the main board. And then, we have Hong Kong and then Shenzhen. But by the end of this year, all the major cities, we have Beijing, Shanghai, Shenzhen, as well as Guangzhou, and then quite a few others. So I think we are consolidating quite well. So we are providing quality service. What I want to do is to provide a platform led by ophthalmologists to provide quality care at an affordable price. So this is what we want to do. And then you look at the name, CIMA as well. C is clinical service. M is model management, E is education, and R is research. Yeah, so we are actually involving in a number of exciting new technology in ophthalmology. Yeah, so thank you for the opportunity to introduce SEMA as well. Thank you.
No worries. Thanks, Prof. It's such a comprehensive coverage of the very, very important thing that has led on from Yoon and Lily, and how the clinical space are looking at how to manage these new technology within the clinical practice. I think that is a very, very important point that you have actually brought up. You have also brought up about China being a very mega country, and that also is a very good opportunity for me to introduce the next speaker, Professor Tin Ong, to say how Singapore, as a 5 million population country, how are we trying to survive in this tsunami of technology from Singapore, and what has SERI, Eye Research Institute, and SNEC has done. And of course, before that, I will just do a quick introduction. Professor Tin Ong is also my dear professor here. He saw me from day one joining ophthalmology. He's my personal career mentors, and he was the ex-president of the Glaucoma Research Society, one of the most prestigious society in the world for glaucoma. And he's got like tons of papers, including in Nature, Genetics, JAMA. And without further ado, let me have Professor Tin Ong to speak and to share some of the things that we are doing in Singapore as well.
Thanks, Daniel. I'd like to thank Daniel and SGInnovate for organizing this symposium, and great talks from Dr. Liu and Dr. Peng. I really enjoyed it. I'm not an AI expert, but at SERI, we were lucky that we have a lot of AI researchers interested in AI and a great talent. And Daniel has formed the AI and Digital Innovation Research Group this year. He's our head of this group. But we also have other professors like Dan Millier, Michael Gerard, and Tyler Rim, who are all working on AI and other solutions. So I think, for us, and of course, our Professor Wong Tian Yin also, who set up the AI platform initially. So of course, for us, we are looking at AI as a future application to help our patients. And we're lucky that we have clinicians who are interested in this area, who are able to apply technology to improve clinical care, and to be able to work out with engineering and AI technical teams to help us move forward. So I think we can't work as doctors alone. Even if we have the best ideas, we need to collaborate widely with our technical teams. And we're lucky that we have two technical teams that we collaborate with, mostly at IHPC at A-STAR, as well as the NUS School of Computing. So this is also very important, to be able to work with these engineers and to be able to speak the same language and to get the same goals. We also have extensive international collaborations. As you know, Singapore is a small country. We cannot have much clinical, we don't have that much clinical volume compared to China, but we're very lucky that we have built up extensive research collaborative networks. And you can see, like Daniel's paper in JAMA 2 years ago, we had more than I think 30 or 40 institutions and multiple collaborators to help us get the required data to have such a high quality work. Yeah, and even like Michael Gerard, he has a network of I think 20 or 30 countries for him to work on AI, on glaucoma, looking at the optic nerve head, and OCT imaging for glaucoma. So this is very important to have such networks. Another, we are fortunate that we have a good technology development and commercialization team at SERI, and they're able to help us navigate through some of this commercialization aspects, including how to form IP as informing companies. And we have one startup company called Iris, from which to help commercialize the technology for diabetic retinopathy and fundus photography screening. So these are very important as well. And I think finally, we're lucky that we have a good link between the research and clinicians and the hospital. So SERI is part of the Singapore National Eye Centre, and we have extremely good links for collecting clinical research information, clinical research data, including a clinical research center with many research coordinators. And this whole thing, it takes many years to build up. And Tian Wong set up population-based studies in Singapore with 10,000 people of different races. And this is now doing a 15-year follow-up. So this also forms a basis for many of our controls. We have good high-quality control data. And we set up an imaging reading center, etc. So all this has helped build up our capabilities over the time. So this took more than 10 to 15 years to get to this stage. Yeah. So obviously, it is a long-term investment and long-term strategy that we are working on. So hopefully that's helpful to you, Daniel.
Thanks, Professor Tin Ong. Yeah, I think that's very helpful. I mean, thanks for sharing the new group that we have just formed, the AI and Digital Innovation Group. As Professor Tin Ong has rightly alluded, our country is small. That's why we have to be extra friendly to a lot of friends from all around the world, because we are always going out to ask for collaborations, data sets, and that's why, I mean, he also personally taught me, sometimes the deal can be taught on the lunch table or the dinner table. So this is something that, unfortunately, this is some of the things that have not put too much advantages on my weight, but, I need to probably, keep physically fit after a lot of the different collaboration stuff. And I also saw quite a few questions that come in through the Q&A. I've kind of summarized it into different big categories here. So, I mean, okay, so we're going to go into the technical questions. Yoon, I'm going to get you to take this. So basically, of all the different questions, they have asked 3 different domains of questions. 1 from technical, 2nd, the black box issues, and 3rd, the reference standard. So I'm going to ask you the technical questions. So is the Google AI research mostly supervised? And is there any unsupervised or semi-supervised learning that you guys are using? And then the second one is, what is each layer is trying to learn? Is it, are we able to know how each of the neural net, the layers within the neural nets learn or extract the features? And is it via the computations? And lastly is the reference standards. The label, can it be a machine learning driven labels? Does it every time has to come from a human expert? So these are 3 questions for you.
Sorry, let me just get it down. So supervised, and then black box, and the reference standard.
Yeah, that's right. So the technical one is it supervised versus unsupervised or semi-supervised? Yeah.
Yeah, so that's a great questions. So first, generally at Google, we do have a research sort of like department that does a lot of research into the foundational machine learning. And so as part of that, we are constantly trying out and developing new techniques for machine learning. One fairly recent one is something called SimCLR, SIMCLR. That is a semi-supervised way of doing machine learning, where the objective is to get the machine learning model to learn what's called a good embedding. An embedding basically means a numerical description of an image that is useful for other applications. So in this case, for example, the technique actually does give you a pretty good embedding that generalizes to different data sets. So I guess the short answer is that we are definitely developing a number of these things. And in terms of use in a more applied setting, though, I think whenever possible, you do need to get a fairly large set of labeled data. Even if not for the training purposes, you do need to evaluate your data on that. And so many techniques do exist to help you reduce the need for labeled data for training. But validation side, you do need quite a bit of data as well. Part of what will help to understand how much data you need can be traditional power calculations. But for that, you do need some assumptions on how good your model is. So that's the supervised question. In terms of the black box, it's a very active area of research to understand how machine learning models actually work. And by machine learning, let me narrow down the answer to deep learning for the moment. There are many machine learning methods out there that are easier to understand just because they have fewer parameters, and sometimes they're fairly transparent about what the parameters are doing. the challenge with deep learning is not that you don't know what the parameters are. You actually know exactly what each of those millions of parameters, the numerical values of each of them are. The challenge is for us to understand what those numbers and computations actually mean. And there's many techniques for this. One technique is called saliency, and that actually encompasses many kinds of techniques, all of which revolve around understanding if your input, for example, is an image, which parts of the image are the most important towards the prediction output. And there are many ways to do this, but generally speaking, that's one category. And another category, which is one of the other visuals that I showed during this slide, is to understand what each individual artificial neuron is doing in the deep learning model. And that visual that I saw was essentially trying to optimize the input that most activates each of the neurons in different layers. And that's how you were getting these visualizations of it learning edges versus shapes versus concepts. The last question I think was about reference standards. I didn't quite catch the full question. Can you remind me briefly?
So the last question is, you know how we usually use the labels graded by the human experts. So the question was, can one day machine learning generates a ground truth in order to train a neural model? Yeah.
Yeah, that's a great question. I think the keywords to search for if you're interested in this domain will be active learning. And generally speaking, in active learning, what you can do is to get the model to create predictions. And so these predictions become, in some sense, like temporary labels for the data set. And then in the process of active learning, you learn which of these examples are the model not certain about. And you only get those data sort of like labeled. The danger in doing any of these techniques generally tends to be around dataset bias. And so essentially what might happen is that you don't know what you don't know. So for example, if the model doesn't know how to deal with a certain kind of image, but it didn't you didn't manage to find out that it's uncertain about those, then you never know about it and you never label it. And so that's one danger of such an approach, but generally speaking, that's a very active area of research as well.
Yeah, I suppose the privileged learning is one of these the areas that's been actively explored as well. Yeah, so I mean, for those who are interested, can actually type privileged learning, and then those are the other areas that's been looked at as well. Okay, so Lily, your turns. You're up next. So 3 questions for you as well. So, I mean, there's questions related to clinical use case related to the Google AI research, the generalizability questions, as well as the commercialization, the questions as being the product manager. So, I mean, the first questions related to the clinical use case. How was the experience of working on fundus imaging for glaucoma research different from the diabetic retinopathy? What different approach was followed than the DR models and data curation and etc.? So I probably would just let you to answer this, and then I'll go on to the second and third so that you can remember what question I'm asking.
Okay, great. Yeah, so I think this is actually a really good question. I really like it because it allows me to actually talk a little bit about problem selection for DR. So versus glaucoma, or problem selection for anything AI related. One of the really critical parts of picking the right problem is actually understanding that the medical community has a good understanding and agreement around how, not only how we diagnose, but also how we treat at each severity. So DR is perfect for this because there are guidelines that are, I mean, they still conflict, but they're generally internationally recognized guidelines, and there's like a handful of them that you can kind of, train the model because there are defined rules. Glaucoma, it's just a lot of art, right, in terms of determining, when people get treated, when people get progress, etc. So I think for glaucoma, it's been a little bit harder for us, and I think there needs to be an agreement on sort of at least when you treat, so that when you're treating the model, at least you could say, okay, well, that's going to be actionable, and so we have tried like proxies that people can agree on really well for certain features of glaucoma. And so you actually end up having this like rubric that is roughly in agreement with a certain group of glaucoma specialists, but unfortunately we still don't have the internationalized, agreed upon kind of version. And in fact, I feel like AGI, like artificial general intelligence, is like probably going to be an easier problem than getting glaucoma people to agree with each other. Just kidding. But that agreement actually is critical to training machine learning models. And so I think that for glaucoma, we might actually have an approach where AI can help get agreement around progression and all that stuff. And then, we can actually have maybe a joint, kind of understanding of the disease, and you can actually maybe use AI to help better understand the progression of the disease and also then get agreement around the grading of the disease.
Right. Thanks, Lee. That's a very good.
Actually, Daniel, can I jump in here?
Yeah, that's why I was about to ask you.
On what level of glaucoma you want to pick up, and if everybody agrees to pick up established glaucoma, then I don't think there's any argument about that. It's only when you want to talk about early glaucoma or suspect glaucoma, that's when all the argument starts about when do you want to start, etc. So, if we try to model our systems to pick up established glaucoma, which is already a big advantage already, because we are missing a lot of people with established glaucoma in the population, I think that will be a head start already.
Prof. Dennis, do you have
great.
any comments on this?
Yeah, I think for diabetic retinopathy, that is a very good starting point. And then for the more complex disease, glaucoma is one area that a lot of demand because, by an experienced clinician or even glaucoma expert, there are still quite a lot of things you may not be able to figure it out, especially sometimes when you look down at the progress for monitoring. So I think this AI is something very exciting that can go beyond human being. So I think initially people are thinking about the AI is going to take up some of the jobs of the human brain. I think it's much more. Yeah, so when you're talking about complex situation, when you're talking about something subtle, and the parameters in glaucoma, I believe there will be more and more coming up. So I think this is really very exciting, and starting from retinopathy all the way to maculopathy, and then optic nerve diseases, so on and so forth.
Thanks. So, last questions to Prof. Tin Nong is, when do you think the consensus of glaucoma definition can be achieved?
There are already some steps ongoing now to come up with a consensus already, and there are several groups working on this. But as I said, for the AI community, I think if we can get established glaucoma, that'll be a head start already, because we are missing established glaucomas in the population.
Right. Okay, guys, I'm very cognizant about time. Now it's 1:15, so we are supposed to end here. I really wanted to take the last opportunity to thank all the expert speakers today, Professor Dennis Lam, Dr. Lily Peng, Dr. Yun Liu, and Professor Tin Ong to join us here today. And thank you so much for SGInnovate for co-hosting this together with us from SERI, SNEC. I really hope that, the audience has actually gained some basic understanding in terms of AI, technical methodology, as well as some of the implementations, barriers, and considerations that when one wishes to use the AI technology within the clinical practice. So with this, I would like to call it a close. And if there's any further questions, please feel free to reach out. I think, Jean, is there any way that we can share some of our contact details, or you could probably look us up at LinkedIn? I think every one of us here has LinkedIn. If not, I think the email address would be another option. Yeah.
So we usually send out a post-event email to all the attendees. So we will be sure to include the LinkedIn contact details of our presenters and our speakers as well. So thank you so much, Daniel, and thank you to all our presenters and speakers. for the great sharing, and everyone for all your ongoing questions. It's always very heartening to see so much enthusiasm in our online sessions, but real conversations often happen after. So we do hope that all of you can keep connected. And we look forward to seeing everyone at the next online event. But for now, if Daniel, you have anything else?
Oh no, I just I'd like to echo what you just said. Like, please reach out, and then hopefully we could meet each other physically, face to face, after the COVID-19 pandemic crisis.
Yeah, definitely. So thank you, everyone, and have a good lunch, and bye, everyone.
See you guys.